All right, welcome to another lab demonstration, or in this case, kind of more of a walkthrough for our 1211 lab. So this is going to be lab 12, and it's kind of a continuation of some of the things that we were looking at in the previous week. Last week, we looked at a lot of examples of drawing Lewis structures and getting information about what does the three-dimensional shape of those molecules look like. This week, we're going to kind of continue off of that a little bit. We're going to talk about something called valence bond theory, or at least kind of the applications of it. The pre-lab video hopefully has done a decent job of explaining a lot of the background information with valence bond theory that you really need to know for everything. And then what I'm going to do now is actually go into kind of the details of how we actually apply that. And so my plan is to do the same thing I did last week. I'm going to have 5 different examples that I've picked out, and we're just going to walk through each example, finding all the pieces that CSE Pub asked for. And so the first example that we talked about last week was PCl3. And so that's the same one I'm going to start with this week as well. And just like last week, your lab packet probably says POCl3. You can go ahead and cross that out. We're doing PCl3 instead. It works better for these kind of things we're focusing on this week in particular. POCl3, it gets a little bit hairy trying to do some of these things, unfortunately, for compounds that have expanded octets and multiple bonds. Some of this idea of hybridization and things like that, unfortunately, just aren't quite as useful or as applicable to those systems. So not going to worry really about that right now. What we are going to look at is kind of what are the basic pieces of applying our things that we're going to be talking about this week. So for PCl3, to really be able to understand and do everything that we want to do this week, our starting point is actually still the Lewis structures. So I'm going to very quickly kind of draw out what the Lewis structure was that we had from last week, and at least somewhat draw it in 3 dimensions. Right, that would be our Lewis structure at PCl3. Now, the different things that we're going to be asked for kind of just in order. The very first thing we're actually going to be asked to do is draw, I think, a valence bond sketch. But I think I'm actually going to do a couple of the things that are like lower down on your little chart for each molecule first, because that will help us draw our valence bond sketch. So the first thing I'm actually going to look at is what is our hybridization. And when it asks for hybridization in your charts, it's always focusing on the central atom for that particular part. Right, so when you see hybridization, it really means hybridization on the central atom. And I'll probably just abbreviate as like hybrid for the future examples that I do on this. But for hybridization, we want to look at our central atom and we want to figure out how many things are around it, right? Because that really is going to help us figure out the hybridization. So if we look at our phosphorus, for a particular phosphorus, there's 1 lone pair of electrons, and then we have 3 bound atoms. So there's 4 total things around the phosphorus. So it has, from last week, a tetrahedral electron geometry. And it turns out hybridization is also very systematic. If you know the electron geometry, you also know the hybridization. So if our hybridization is tetrahedral, then what's going to happen is for our hybridization, we're going to get sp3. And that's because, again, there's 4 things around the phosphorus. And if you're trying to figure out like how, what hybridization things take, one of the easy things I like to associate that helps me keep track of it really easily and quickly, however many total things are around your particular atom that you're looking at, for the hybridization, the number of things around the atom is the number of orbitals involved in that hybridization name. So in this case, if we have 4 things around the phosphorus, it's sp3, because with 1 s orbital and 3 p orbitals, it's 4 total. So there's the 4 that we have around our phosphorus. And so that's one of the ways I like to kind of look at how do we assign these hybridizations, or ways to think about it and remember to do it hopefully kind of quickly and easily. All right, after figuring out the hybridization, one of the other things you're going to get asked about is the number of sigma and pi bonds. Right, and so this deals with the different types of bonds in molecules. And for sigma bonds, they're pretty easy to pick out because they're just the first bond between any 2 atoms. All single bonds are just sigma bonds. And so in this case, our molecule has 3 single bonds, so all of them are going to be sigma. Right? So in this case, we're going to have 3 sigma bonds, and there's no pi bonds because pi bonds only show up in multiple bonds. Like if we have a double bond, that double bond would contain 1 sigma, which is the first bond between the atoms, and 1 pi bond, which would be then any additional ones. So like a double bond would be 1 sigma, 1 pi, a triple bond would be 1 sigma and 2 pi bonds within it. But again, in this case, no multiple bonds, so there are no pi bonds that are going to be present. So we have 3 sigma bonds, 0 pi bonds for this molecule. And now, having thought about that a little bit, now I think it's easier to go into the valence bond sketch. So the next part of this, we'll take a look at drawing a VB sketch. And I'm going to actually move this up a little bit just because I know this is going to take up a little bit of space to actually draw. And for our valence bond sketches, it's important because to always kind of have a good starting point. And I think the best starting point is usually going to involve finding what is your electron geometry, and just for whatever that electron geometry is, always draw that same kind of version as a starting point. So if something is tetrahedral, always draw the same thing to start out with, and then go about attaching all the other pieces. So in this case, we have that center phosphorus that is tetrahedral. It's sp3 hybridization. Anything that's sp3 hybridization, our starting way that we usually sketch it is going to look something like this. If you've ever had Dr. Herbert for anything, he will often affectionately refer to these as chicken feet, because that's really kind of what it almost looks like. Really, in effect, what this is, these are our 4 hybrid orbitals around the phosphorus, just arranged in a tetrahedral fashion. But since we're drawing the orbitals, we can't really use wedges and dashes to show the three-dimensional nature of things. So you just kind of have to keep in mind that this is really meant to try and show the three-dimensional orientation in space, is why it's being drawn that way. Now, the next piece of this for our valence bond sketches, we found the hybridization, that sp3, right? If I scroll back down just a touch, we found the sp3 hybridization on our phosphorus. But to do the full VB sketch, we actually want to know what's the hybridization on our outer atoms as well. So if we look at each of these chlorines, this chlorine has 1, 2, 3 lone pairs and 1 bound atom, so it's 4 things around it. And really all the chlorines look the same. So all the chlorines also have sp3 hybridization in this case. And what we want to do is actually then draw each of the chlorines so that they have sp3 hybridization. But we're going to do so in a way that lets at least one of those hybrid orbitals overlap with one of the ones on the phosphorus. And again, I'm going to have to scroll down just so there's plenty of space here. And so as a kind of a warning as you go to draw these on your paper for what you want to eventually take images of to turn in, leave yourself plenty of space to make the valence bond sketches, because a lot of them can be very large. And so we just want to make sure you have plenty of space to try and be able to put these things together. And we're not expecting the prettiest of artwork. As you can see here, my own artistic skills are pretty limited, so I'm just trying to do the best I can of actually just showing all of the pieces that are being there, and that's all we're going to really expect out of you guys as well. And so in this particular instance, what I'm looking at here, I've now put basically these sp3 hybrid orbitals on all of the chlorines, and the only thing that's really left for me to do is any spots where there's overlaps, and then any other just additional orbitals that don't have overlaps, we want to add electrons. Right, and so if we think about this, the phosphorus is going to have, oops, I've actually messed up my drawing here. So this will be a good kind of lesson point here. I'm going to get rid of that chlorine that was on top, because there's only 3 chlorines here. It is just PCl3 that we're looking at, right? So PCl3, if I'm looking here, there's my structure. I apologize for that. I accidentally got ahead of myself, drew an extra chlorine there that didn't need to be there. So this is what my structure should look like in terms of all of the 3 chlorines there. Everything's kind of now attached to them. It actually nicely shrinks things down for us a little bit too. And what I'm going to do is add those extra electrons. So I can start by adding my lone pair up here on the phosphorus. And you notice each of these chlorines have 3 empty orbitals. Well, why do they each have 3 empty orbitals that don't overlap? If we go back to that Lewis structure, right? Our Lewis structure, each of the chlorines has 3 lone pairs. So all the lone pairs are there. And so you should see those kind of things line up every time we look at our examples for this lab. So when you're drawing a valence bond sketch, however many lone pairs are on a particular outer atom specifically, and even the inner atoms, also the central atoms, you should always have basically these orbitals that aren't doing anything with anything else equal to the number of lone pairs something has, because that's where the lone pairs are. So I'm going to draw this down just a little bit, or drag this down just a little bit. So to finish this out, again, I'm going to put the rest of my electrons in. All the chlorines have those lone pairs on the outsides. And you can just do your best to add the pairs here. Obviously, it's going to be somewhat difficult to make it really easy and visible as I add all of those pairs, and you see me kind of like filling them in down here. And additionally, any spots with overlaps, we're also going to try to add pairs in. And so I'm going to put my dots in here. But again, this is I am somewhat artistically challenged in terms of trying to show this, trying to draw on an iPad and kind of make this very clear. But we just want to see like the pairs of electrons showing up here. And it doesn't have to be perfectly clear. It doesn't have to be perfect like images or anything like that. What I have here, just if you can show that there's something here in the overlap, like every spot there's an overlap, those are the electrons being shared basically in these bonds. Is how we're trying to draw them. So at this point, now that I have all my electrons in these bonds and in all the empty orbitals for lone pairs, now I'm done with my valence bond sketch. That would be everything. And you might not draw these a ton for your lecture classes, but they are kind of useful to kind of go through the process and actually think about like actually seeing the lone pairs and kind of the types of orbitals that are involved for these things. And as you go on to organic chemistry, you will actually look again at kind of some of these orbital pictures in terms of what orbitals are interacting and forming bonds in molecules. All right. Now, there's a couple last pieces that we also want to take a look at for this molecule. I'm actually going to scroll back down so you can see our full Lewis structure too. And the last pieces have to deal with polarity, right? So polarity, we have two questions that the lab packets ask us for each of these molecules. The first one asks us, are there polar bonds in the molecule? And so our quickest way to really think about polar bonds is as we look at our molecule, are all of the elements the same or are they only carbon and hydrogen? Because if either one of those questions, if their answer is yes, then we're going to consider it there's no polar bonds in the molecule. Because if all of our elements are the same, they all have the same electronegativity, there's no polarity in those bonds. Carbon and hydrogen are probably the only two elements we would expect people just offhand to know make a nonpolar bond. There are other combinations that do it, but really for the purpose of this lab and really just kind of in general, unless we give you a table of electronegativity values, we probably would just expect you to treat every bond between different elements as polar. And like I said, unless there's something else there to kind of tell you that's not the case. But carbon-hydrogen bonds in particular are considered nonpolar. It's actually kind of the foundation of most of organic chemistry. And so that is something to just kind of keep in mind. If you see carbon-hydrogen bonds, those are nonpolar bonds. In this case, we have phosphorus bound to chlorine. Well, these are different elements. They're not carbon-hydrogen bonds, and so this is going to have polar bonds included. And so it's really just kind of like a yes or no situation. So for the question of polar bonds, the answer would be yes. And then we also have a follow-up question that's going to involve, is the molecule polar? Do we have a polar molecule or not? And so this is the part that's a little trickier. Because what we're going to do is for each bond in our molecule that is polar, which in this case are our 3 phosphorus chlorine bonds, we're effectively going to draw what we call a dipole. And so I'm going to draw this into the Lewis dot structure sketch that I have here. And these dipoles are typically arrows that have a plus sign on one end, kind of on it's on kind of the opposite side of where the arrow is pointing. And really, those arrows are pointing towards the more electronegative atom in the bond to kind of show where the charge is kind of going, or where the electrons are kind of getting pulled towards. Now, to figure out if a molecule is polar, what we really try to do is take all of these dipoles and add them all up together to see if they cancel out. Unfortunately, one of the things that gets tricky with this molecule is three-dimensional, right? It's not flat, which means these little dipoles that I've drawn aren't particularly accurate just by looking at them to try and see how well they cancel out. Now, there are some quick things you can notice. If all of my dipoles are generally pointing downward and there's nothing pointing back up to cancel them out, that means they all can't cancel. And that's really actually all we care about. If all the dipoles do cancel out, that's when a molecule is nonpolar. But if the dipoles don't cancel out, that's what makes a molecule polar. So in this case, since all of these are pointing down a little bit, that is going to end up making our molecule polar with what we call a net dipole, which is some dipole left over that hasn't been canceled. We'll have a net dipole that will point down for this molecule, the way I have it drawn there. Now, one of the other things I think that's really helpful is to think almost kind of like just symmetry and pattern based. Anytime you have a lone pair on your central atom and your bonds are polar to start with, you probably have a polar molecule. There's only a couple exceptions to that. The main two being if you have something that is linear or if you have something that's square planar for your molecular geometry. Those are kind of the only times that could possibly happen. So there's not very many situations where that's really going to come up. So more often than not, if you have a lone pair on your central atom and you have polar bonds, your molecule is probably polar. Like I said, there are those two molecular geometries that could be exceptions, but other than that, everything's going to be polar. So in this case, we have a lone pair here that effectively breaks up our symmetry, because if we did have a chlorine up there, like I started drawing when I drew that valence bond sketch, if there was another chlorine on top up here, then we would actually see at that point all of our dipoles cancel out, because the dipole going up to a chlorine and kind of where that lone pair is would end up kind of canceling out the downward dipole of the other three dipoles combining, and they would all actually cancel out. All of our electron geometries are symmetric in a way where that would happen if we have kind of the same thing in every direction around that atom for one of our electron geometries. In this case, though, we don't have that. So for our polarity, our molecule is polar. And that's it. We don't have anything else to worry about there. All right. So that wraps up, I think, all the pieces for this first example with PCl3. So I'm going to scroll down and give myself some more space. Maybe give you a second to kind of make sure you got everything kind of down for this particular one. And then I'm going to go down and we'll take a look at the next example that we had done from last time. And so I think the second example we took a look at last week was carbon dioxide, CO2. And so we're going to take a look at CO2. First thing we'll need is the Lewis structure. So I'll put that up here real quick from last time as well. So there's our Lewis structure from last time. And now I'm going to go through things kind of in the same order I did before. So the hybridization I'm going to do first. And again, hybridization for the box in our lab packet is always about the central atom. So we're going to look at the central atom and we want to figure out how many total things are around it. Well, even though it's got 4 bonds, there's only 2 actual things around the carbon in CO2. And so if there's 2 things around the carbon, there should be 2 orbitals in the hybridization name, which means it's going to be just sp. Right? 1 s orbital and 1 p orbital will give us the sp hybridization for this particular molecule. Now, something else that you can kind of keep in mind as well that can sometimes be helpful. Anytime you don't have all 3 of your p orbitals involved in hybridization on a central atom, the only reason that would ever happen is if you have multiple bonds. And basically, every what we call pi bond, right, and then we'll kind of get to in just a second again too, every pi bond that you have, that's going to be 1 less p orbital that hybridizes, because our pi bonds only happen if we have plain p orbitals. So a lot of these things, once you kind of get a bigger picture, I think, understanding of them, it kind of all comes together and makes sense with each other, but it does take a little bit to get there, so I understand that. So kind of heading in this direction, I also want to then we'll label how many sigma and pi bonds we have in this molecule, right? And so for the sigma bonds, right, the first bond between 2 atoms is sigma, right? So we have 2 double bonds, so that'll be 2 sigma bonds, which is the first of each of those double bonds. And then we'll also have 2 pi bonds, right, which is the second bond in each of those double bonds. And like I said, since we have 2 pi bonds, that means there has to be 2 p orbitals on our central atom that don't hybridize, which is why that central carbon then has sp hybridization, because the other 2 p orbitals have to make those 2 pi bonds. And we should always kind of see those things line up. And we'll see that in the next example, actually, with nitrate as well. All right. Now, next piece of this then, after we have our hybridization, our number of sigma and pi bonds, I'll do the valence bond sketch again. Got hopefully plenty of room on this one. It's a little bit easier to do from a just total space standpoint. But it is still going to look a little bit different because we do have pi bonds this time. So how we normally sketch things, again, for the valence bond sketch, look at what hybridization you've given your central atom and kind of look back at what we had in the pre-lab, like how do we normally draw like an sp hybridization? And if we think about sp hybridization, the way we normally do that is we're going to take our central atom, which in this case is our carbon, and we're going to draw our hybrid orbitals pointing in the direction of where our atoms are that this carbon is going to be bound to. And then we're going to draw lines for any p orbitals that remain that aren't hybridized, which we're going to have 2 different lines that we're going to do that with, right? So in this case, one that would be going up and down, and one that's kind of coming in and out of our page here, out of our screen. And so that's kind of why I've angled it that way to show that it would be really coming in and out. And so now we want to add our outer oxygens. But as we do that, we also want to think, what kind of hybridization do these outer oxygens have? Well, if this oxygen here has 2 lone pairs and it's bound to 1 atom, that's only 3 things around it, which means that each of those oxygens is going to have sp2 hybridization, right? 3 things, so sp2, the 3 the 3 orbitals that will hybridize. And the other thing there is, notice this oxygen has one multiple bond that it's making, and because of that, that's going to be the one p orbital that doesn't hybridize, right? Because it needs that p orbital to do that. And we'll see that actually in the sketch. But for sp2, how we usually draw that is 3 hybrid orbitals, and then one, again, line for our p orbital that didn't hybridize there. And then I'm also going to have one more oxygen on the other side that also has sp2 hybridization. So again, I'm going to have kind of my 3 hybrid orbitals. And again, my sketch here is already looking a little wonky, so I'm gonna clean this up a little bit on this side over here. Try drawing that one more time. Oxygen. And you're going to notice something different. On this oxygen, I'm actually going to draw my unhybridized p orbital at a bit of an angle there. Because we're going to see here for this other oxygen, when we want to connect our pi bonds, the pi bonds are actually, instead of orbitals overlapping with just kind of those lobes, the pi bonds are going to connect and make kind of these boxes to show really this is a p orbital kind of going in both of these directions, and it's overlapping in 2 spots, right? Which is something that's characteristic only of pi bonds. Sigma bonds are a direct overlap that only overlap in 1 spot. And so this visually is actually showing that kind of representation. And so the other pi bond we can also connect to fill in and kind of make our box. And now the only thing that should be left is just adding all those electrons, right? For the boxes and pi bonds, we can't really add dots, so we actually add our up and down arrows for our pair of electrons. So we'll do that. We can put our, or at least try to, add our little dots. Kind of tried to add my dots in here for my 2 sigma bonds. And then also notice we have these 2 empty orbitals on each of the oxygens, which, lo and behold, matches the 2 lone pairs that they should each have. So our lone pairs go in those leftover hybrid orbitals. And that should be now all of our electrons added to this sketch. Now it should be everything for our valence bond sketch. Now, notice we have 2 different double bonds in this molecule, so we end up with 2 totally separate boxes that are not kind of overlapped with each other in any way. And they are perpendicular to each other like you see there. That is the actual orientation those things will have. Make note of that because the next example we see will be a little bit different when we look at nitrate, which has resonance. And resonance gets represented slightly differently with these valence bond sketches. And like I said, we'll see that in our next example. Now, the last thing here, dealing with polarity. So we'll ask ourselves, do we have polar bonds? Well, we have carbon bound to hydrogen. I'm sorry, carbon bound to oxygen, excuse me, which is not hydrogen. So we have carbon-bounded elements that are not itself. It's not hydrogen, so these are going to be polar bonds. But if we think about the dipoles, this is one we can actually see because we can actually draw it in 2 dimensions, right? We have dipoles that are exactly opposite of each other, so they are going to cancel out entirely, which means in terms of the whole molecule is not polar. Right? There's no net dipole because those 2 dipoles being opposite will cancel each other out. So we consider this then a non-polar molecule, or you can say it's, for like the polar molecule question, no, it is not polar. All right, so that should be everything then for CO2. So we can see, we've now seen kind of what happens with double bonds for some of these valence bond sketches. So our next couple examples, we're going to take a look at, I think it's nitrate next, NO3 minus. And so again, I'm going to leave this here for just a second, and then I'll scroll down and start the nitrate example. Nitrate's going to be the only example we see here that has resonance in it. And so now that we've seen the double bond side of things, we'll see how does resonance look with respect to those double bonds also, because it is going to look slightly different. All right, so I'm going to scroll down, and we're going to start our nitrate example. So we have NO3 minus for nitrate. Lewis structure from what we saw last week. Right, looks something like this. Only it's a little bit more complicated, right? Because this is just one resonance form. This is not all of them. When I say resonance, remember that's because this double bond could also be here or here. It can kind of rotate around. And something that to keep in mind when you see resonance, I don't think I remember if I covered this in the lab demonstration video last week. I think I talked about it in the pre-lab video though. When you do have resonance like this, what really ends up happening is you don't see a double bond just here. You actually end up seeing for all of these bonds, they all kind of get averaged out to be equal with each other. And so really each nitrogen-oxygen bond is not really a single bond or a double bond. It's kind of like an average in between. And since you have one double bond being spread across 3 places, it's really like 1 1/3 bonds between each nitrogen and oxygen. It's kind of how that resonance works. And we'll show that actually a little bit in this valence bond sketch that we're going to get to, because it will look different than what we saw in that CO2 example. But before we get there, we'll answer our questions about hybridization and sigma and pi bonds first. And again, that will hopefully help kind of paint a picture for us of helping us get started on that valence bond sketch. So for the hybridization, we're going to look at our central atom. We have our nitrogen here. And what we're going to do now is we're going to count how many things are around it. We have 3 oxygens. There's no lone pairs in the nitrogen. And again, the fact it makes 4 bonds, don't care. It's only got 3 actual things around it. So if there's 3 things around it, there should be 3 orbitals hybridizing, which means the nitrogen is going to have sp2 hybridization. All right. Next, we're going to take a look at sigma and pi bonds. So for the sigma bonds, again, first bond between the 2 atoms is sigma. So here's 1, 2, and we get a third one for one of the 2 bonds in the double bond. And then for our pi bond, there's going to be 1 because we have the 1 double bond where the second bond is a pi bond. And again, this should kind of make sense. If we have 1 pi bond, that's 1 p orbital that shouldn't hybridize. That's why it's sp2 and not sp3. Again, just kind of trying to keep those things kind of connected together nicely. All right, so the next piece of this, we're going to be taking a look at trying to draw our valence bond sketch. So we're going to start with the sp2 kind of sketch of things. Sorry, I'm trying to clean something off my screen here if you see things moving around a little bit. So for the next part of this, we want to draw our sp2 hybridization, just kind of general setup for our nitrogen. And I'm actually going to scroll this up just a touch, simply because the sketch is going to be reasonably sized. And so I want to leave myself plenty of room to hopefully make this example clear. So I'm going to start with our nitrogen. And for sp2, we have 3 hybrid orbitals. And then our 1 unhybridized p orbital is how we're going to draw that. All right. Now for all of our outer oxygens, this is where resonance gets a little strange, right? So I've said, I'm going to come back up here, for each of these oxygens, since the double bond could be at any of those spots, we're going to draw them in the valence bond sketch as though they have whatever hybridization they would take if they did have the double bond. And so here's how we're going to kind of go ahead and show that. So here is our oxygen. We're going to give it sp2 hybridization for this first one. That'd be the one that has a double bond here. But for the others, we're also going to give them sp2 hybridization. And we're going to see what that kind of ends up doing to our overall sketch here in just a second. Right, and each of these is also going to have an unhybridized p orbital. And now what we're going to do to put everything together, the biggest difference between the pi bonding that we saw in the previous example and this one is that we're going to connect the boxes to all of the oxygens. Right, there's only 1 pi bond in this molecule. Right, that's what we've stated here is there's 1 pi bond. But that nitrogen in its 1 p orbital that can make the pi bond is actually interacting with the p orbitals on all of the other oxygens. Right, that's really kind of almost what resonance means, is that 1 pi orbital, or the p orbital, on your central atom is interacting with the p orbitals on multiple other atoms at the same time. It's not that common that happens, but there are molecules where that does happen, and that's just kind of the most stable way that they can really kind of configure themselves. I'm going to clean up this bottom oxygen just a touch, because looking at it kind of with that 1 hybrid orbital looked a little strange. And now all that's left is putting electrons in. And so this isn't the perfect way of kind of showing the electrons in terms of just having the right total numbers of things. But I am going to go ahead and put all of these electrons here in the pi bonds just because we've shown them that way, just so that our total number of electrons is correct. However, the reality is, I'm going to kind of apologize for the 2 electrons over here looking a little strange. The reality is that there's really only 2 electrons total that are making a pi bond, even though the way this image looks right now does kind of have 6 the way it's drawn. So it is a little bit strange in terms of total number of electrons here. There's really only 2 electrons overall that are actually involved in all of this resonance. So I do want to kind of emphasize that some. But because we've drawn each of these with sp2 hybridization, like if there was a double bond here, these wouldn't be here. They'd be in like another lone pair, and these would be sp3 hybridized. But that's not really how resonance works. It's a little more complicated than that, unfortunately. And so this is how we would draw the resonance. And I do want to scroll back up to kind of compare this to the CO2 example we saw a second ago. Notice in CO2, we had two different pi bonds. So we had completely separate boxes that weren't really attached to each other. But for nitrate, since we have that resonance, we actually have all of our boxes all connecting to the same line on the central atom. And that's how you can kind of tell the difference between resonance and just having multiple pi bonds on a central atom. All right, there is one thing left for this molecule, and I haven't left myself a ton of space to really answer that, but I think I can squeeze that in here. I'll actually try zooming in a little bit here to give myself some space. So we're going to ask, is this molecule, or does this molecule have polar bonds? Yes or no? And then is the molecule polar? Right, our last two questions. Now, I'm going to give us a look at our Lewis structure here. If we're looking at our Lewis structure, remember with resonance, all of these bonds are actually equal to each other, which means we have no lone pairs in the central atom, and every single thing around that central atom is the same, which really means everything is symmetric. We do have dipoles, right? We'd have dipoles pointing towards each of the oxygens. And since this molecule is flat, we can actually really try to add the dipoles if we wanted. So we have one dipole that's going up. And the way you usually add dipoles, or I show it, is you can do something called the tip to tail method. So where this first dipole ended, I'll start drawing the second one. So let's say we go down to the left next. And where that one ends, I'll start drawing the last one, which would go down to the right. And what we really notice is, basically, I ended up where I started right there, right? Anytime you end up where you start, that means all your dipoles canceled. So if all my dipoles canceled, I actually kind of skipped the polar bonds question, but that makes our molecule as a whole non-polar, right? It's not going to be a polar molecule because all the dipoles canceled. Now, I have shown dipoles, right, between the nitrogen and oxygen, so the answer to this first question, do we have polar bonds, is still yes. We have elements that are not the same element. It's not a carbon-hydrogen bond, so they are polar bonds, but they do end up canceling all of the dipoles. All right, so I'm going to try to rezoom things to fit a little bit better here again. All right. So that should be everything for our nitrate example. Again, I'll leave it here for just a couple seconds. Our last couple examples that I'm going to take a look at are just to help us see what the valence bond sketches are going to look like for some of our other geometries that we haven't seen yet. So for instance, like trigonal bipyramidal and octahedral geometry types. So that'll be what we move into next. All right, so the next example that we're going to take a look at then is going to be triiodide, I3 minus. And from last week, what this thing looked like for a Lewis structure was this. Right, we did have 3 lone pairs on the central atom as well, which gave that central atom a negative formal charge. And so that was our Lewis structure from last time. Now, to answer our questions that we've been going through for all of these so far, I want to look at hybridization, sigma bonds, and pi bonds. So for hybridization, what we're going to take a look at, central atom, how many things are around it? So if we're looking here, right, we have 2 bound atoms and 3 lone pairs. It's a total of 5 things. So for our hybridization, that means our hybridization is going to have 5 orbitals involved in its name. So once we've used, like for sp3 that we saw earlier, that was 4, but we don't have more than 3 p orbitals, right? And we don't have more than 1 s. That's why we never see more than 1 s orbital in these hybridization labels. So if we've used all of our s and p orbitals, the next orbital type is d. And so the way we label this then would be sp3d. Oops, let me scroll this down just a touch so it's visible there. Sorry. So sp3d would be our hybridization label. Now for our sigma and pi bonds. For sigma, if we look here, we only have single bonds, so all our bonds are just sigma, which is 2 in this case, and no pi bonds because there are no multiple bonds. All right, for our valence bond sketch. The good news, if there's no multiple bonds anywhere, the valence bond sketches usually aren't all that complicated. The bad news is some of them can take up a lot of space. This one's not too bad. but the next one actually will look pretty large. So for this one, I'm trying to give myself plenty of space here still. I'm going to draw my central iodine. And when I go to draw this, for trigonal bipyramidal or this SP3D hybridization, we draw this basically with our somewhat trigonal bipyramidal. I'm going to just make this one a little bit clearer for kind of my own OCD sake. So we're just drawing our hybrid orbitals in all the directions of a trigonal bipyramidal geometry, or as kind of best we can to that end. Now, for this geometry, there is one thing that's important, right? Trigonal bipyramidal has different locations. We have the axial positions going up and down, and the equatorial positions making kind of that trigonal planar part that's perpendicular to the linear part. So lone pairs versus the bound atoms, where each piece goes does matter for this structure. For all the other ones, it doesn't. Like if I go all the way back up just for a second to our first example that we did with PCl3, like I could have put a chlorine up here and put the lone pair down here, and it would have been the same thing. It makes no difference because all of these spots for a tetrahedral geometry are the same. But for our trigonal bipyramidal geometry that we see here in triiodide, that's not the case. So for putting the pieces onto this one, what we're going to do is our lone pairs, remember what we said last week, lone pairs have to go in these equatorial positions. So that's where the lone pairs are going to go on that central iodine. So there's our 3 lone pairs on those. And that means our 2 iodines actually go in what we call these axial positions. And for their hybridization on the outer atoms, each iodine has 3 lone pairs in 1 bond for the outer ones. So it's 4 things, so sp3. So we get kind of our little chicken feet look to those outer iodines. We can add, and again, I haven't left myself a lot of overlap room, so I'm going to draw just a pair here. Relatively large dots on each side for my bonding pairs. Then I have my lone pairs in the outer atoms that I'm drawing and trying to add in here as best I can. So there's all these lone pairs. And that's it. There is nothing else, right? I don't have to worry about any pi bonds in this molecule. So really the biggest thing with if you have just sigma bonds and these expanded octet systems, they're oftentimes just kind of large. And you notice I didn't leave myself a ton of room in some of those overlapped areas to draw that really easily. That's okay. Like I said, these drawings don't have to be perfect when you turn them in. They just need to be enough that we can kind of see that you put everything in them. And that's really what we're looking for. So that would be it for the VB sketch on triiodide. So what's left is the polarity questions. So on this one, first question is, do we have polar bonds? And so in this case, all of our elements that are involved are the same, right? They're all iodines. So if they're all iodines, then this molecule doesn't have any polar bonds because they all have the same electronegativity. Now, it is true we do have a partial negative charge here, but one thing to kind of keep in mind when you have polar molecules, in terms of having polar molecules, which is kind of the end goal of really asking this polar bond question usually, for us to have a polar molecule, you need basically a positive and a negative end to the whole molecule. In this case, the negative's kind of in the middle, and that's just it because the whole thing's negative anyway. And so there's not necessarily like an end to the molecule that's positive and another end that's negative. And so it's not really going to be polar. Instead, and I think the easy thing here that we will often kind of associate with an example like this, if all these elements are the same, then there's no polar bonds. And if your answer to the polar bond question is no, whether the molecule is polar or not is really easy because the answer is always no. So if there's no polar bonds, your molecule is also not polar. And that will always be the case. There are 0 exceptions to that part. So triiodide, even though it has a charge, it is nonpolar in terms of how we normally think about it, simply because there is no kind of positive or negative end. The nitrate example that we saw earlier actually follows kind of that same suit. There's partial charges that are being kind of shared around everywhere, like that. The nitrate, if I actually scroll back up to it for a second, like the nitrate example here, because the resonance is shared everywhere, there's a kind of negative charge all around the outside. But because of that, there's not like one end that's positive and one end that's negative on the outer parts. And so it's not actually polar because there aren't full-on different charged poles to the molecule itself. All right. So one last example that we're going to take a look at, kind of going through our full process for here. And so our last example from last time was SF6. And so Lewis structure for this one looked like this. And I still have 2 more fluorines to go. And so all of those fluorines have a single bond. They all have 3 lone pairs, although I kind of jammed that last one in there, unfortunately, a little bit. But they are all kind of the same in terms of how they look. Now, to answer our kind of same line of questioning that we've been going through, I want to figure out what's the hybridization on our central atom. Well, if there's 6 total things around the sulfur here, that means there's 6 orbitals involved in hybridization. And again, anytime we're past 4, we need more than just S and P. So this one's going to be sp3d2. Right, and again, I cut myself off here. Sorry. So sp3d2 for our hybridization. And now for our sigma and pi, this one also, again, I think hopefully should be pretty easy. And really, the sigma and pi, once you kind of get them, as soon as you see the Lewis structure, they're really easy. Right? In this case, everything's a single bond, so everything's just a sigma bond. We only have to worry about the pi if there's multiples. So in this case, 0 pi bonds, 6 sigma. That part's pretty easy. And now the valence bond sketch part. So again, I'm going to scroll myself down here just to give myself plenty of room because this one is going to be fairly large. Right? It's not necessarily going to be, I think, hard to draw. It's just it's going to take up a lot of space. And so if I scroll down a little bit here for this, I have sp3d2 hybridization. Anything that has that hybridization, we always basically just draw all of our hybrid orbitals in the relative shape that we would for an octahedral compound, like for an octahedral Vesper sketch. And I might try to clean this up just a little bit because my orbitals don't all look all that similar to each other. It's a little bit better, still not perfect. Apologize. I will never make a career as an artist, so I've come to terms with that, unfortunately. But if this is our octahedral geometry, like right, we have our 6 different hybrid orbitals all oriented in a semi-octahedral shape. Now we're just going to add our outer atoms. Now to do that, if I scroll back up to our Lewis structure again quick, we do want to know the hybridization of all the fluorines, but this should look familiar now, right? We've had halogens as outer atoms before that are just 3 lone pairs in a bond, which we said before it was sp3, so it's still sp3. So all of these outer fluorines are going to have sp3 hybridization. And this is the part that's going to make this, like I said, kind of large. I'm going to do my best to kind of fit everything here. And keep in mind, I've drawn these a bunch in the past, and even I sometimes scrunch these things in ways that it's not the best looking drawing in the world. So that just goes to further iterate my point that we're not going to be super picky on how pretty your drawings are. We just want you to have all of the major details that we expect to see. Right, so there's all 6 of my fluorines in the outer atoms. They all have the overlaps now with the sulfur. So there's a bunch of sigma bonds. I'm going to just make big dots for the overlaps here for the lone pairs that are in the bonds, simply because I'm not drawing this big enough on my iPad to easily fit the lone pairs in there. Still fine. And then there's 2 electrons in every one of those outer orbitals on the fluorines. That's a lot of little tiny dots in these outer orbitals. But I'm doing my best to try and make sure they actually show up. That should be, I think, all of them. And now all of that stuff's filled. And again, since there's no multiple bonds, that's it. There's nothing else to add for a valence bond sketch here. Like I said, it is large, it's bulky, it takes up a lot of space, but it's not necessarily too bad to go through and actually draw. I think it's where you have multiple bonds, that's where things get a little bit trickier for some of those VB sketches. Now, last 2 questions. Polar bonds and polar molecule. So for the first part, polar bonds, we have sulfur bound to a bunch of fluorines. Fluorine is very electronegative, so yes, all of these bonds are quite polar. But if we look at the symmetry of our molecule, We have a fluorine to the left and a fluorine to the right, so dipoles there are going to be opposite. We have a fluorine above and a fluorine down, so dipoles there are opposite. And we have a fluorine going, really this is kind of straight back into the page, kind of away from us, and one straight out of the page, out towards us. Those are also opposite, and they're going to cancel. So really all of our dipoles are actually going to cancel. So even though we do have the polar bonds, notice there's no lone pairs in the central atom to break up any of the symmetry of the shape. And so the actual molecule itself is not polar. It's going to be a non-polar molecule at the end of this. All right, so that's going to be, like I said, this going to, I think, covers all the same examples now that we saw last week in terms of the different questions that we wanted to answer for this week. So kind of go through the rest of the packet. You're basically just doing the same things that we just did here. And the last couple things I'll say just deal with kind of uploading this assignment and the previous weeks, just to kind of remind people. You will have to go to CSE Pub's page and log in to actually turn in your assignments there. There's not links in D2L for the Lab 11 and 12 assignments for, I think, there might be one or two sections that we're able to add them, but I think for the most part, we didn't do that for most of them. So you're probably going to have to go to CSE Pub. The website, just go in there. You can still find, like, if you first log in to your course page on CSE Pub, you'll have kind of like something that's like the lab reading, then you'll have one that says like lab assignments. Go into lab assignments and go down. You can find lab 11 and lab 12. Click those, and that basically when you open those up, they should have one question for the whole assignment. And it's basically a question where you can upload a document with all of your images for the lab. So you can either scan them, if you have a computer that, or a printer or something that can do that. If you can't, you can take individual pictures of each of your pages and then just copy them all and say in like a Word document or something, and upload them that way. If you do have any issues with this process, please reach out to your instructors, reach out to myself, and we can try and help with that process in any way we can, just to make sure you can get everything kind of turned in for this particular lab. It's a little bit strange and different, I know. This is not one that was traditionally graded through CSE Pub. It used to be handed in just manually, but we unfortunately don't have that luxury this semester. So if you do have any problems with that, please let us know. Otherwise, I will be back here with another video here in another week or two for our last actual lab experiment, which is the Charles Law Lab. And so I'll have a video for that one, and I'll probably try to have at least a little bit of a clip on some things to help maybe review for the final exam, because that's going to sneak up pretty fast on us here as we get towards the end. Because what we would have had planned if we were face-to-face is for, we would have had a week that had basically like an exam 4 review that was also kind of like a final exam review to kind of couple the two together. We don't have the in-face review this time, so I'll make sure instead that we'll actually spend some time kind of going over some things to expect so that everyone kind of knows what's going to be coming for the final once our department kind of has that kind of squared away and finalized as well. All right, that's all I have for this week. Like I said, if you have questions, reach out to us. Otherwise, I will see you next time.